Okay, so before starting my talk, I'd like to to provide some context about uh, who I am and why I am here, and I guess how my path has crossed Doug's path, and also some context for the talk that I'm going to give. So I did my PhD in combinatorial aspects of code, and in particular, algebraic association schemes of codes following the work of Philippe Delsart. And then, but quickly, and generalized designs and things like this. But then quickly I moved to cryptography, and that is what I've been doing since then. So if you look at cryptography at 10,000 feet, you can say cryptography it has two camps. So on one hand, you have computational cryptography, where your security comes because the adversary does not have enough computational power. So it cannot compute enough, and that is why you get your security. Now, and the other camp is this information theoretic security, where the adversary can have infinite computation, all computation of the world, and all future computation, but still he cannot achieve their goal because there is not enough information. So this is these two camps. And then when you look at how we approach security, cryptography actually, we start with a model. So we try to make a model, an abstract model of what we want to capture. Then we define security, what is the notion of security that we are interested in. We also define some measure of efficiency, because if there is no efficiency, then everything can be done. So we also define some measure of efficiency, and then we try to prove results, say what is the relation between these parameters, and then what are the bounds. And we also make constructions. And so when you are in information theoretic camp, you have the kind of bounds that you saw this morning, and then you have constructions that can achieve those bounds. And those are optimal constructions. And these optimal constructions, they are very elegant, and usually they use a lot of combinatorial structures. So, and that is where I've been doing a lot of work, spending a fair bit of time on that domain. And I think this is where also Doug's work became very much important to me. And so, of course, so yeah, we have heard a lot about Doug's contribution to designs and the Steiner system yesterday. Today, we saw some of his work in cryptography, but I think his book, which is now in 4th edition with Maura as a co-author, it's been one of the earliest book that we have in classical cryptography, in particular information theoretic cryptography. Of course, he has also numerous impactful papers on things like universal hashing, orthogonal arrays, that I've been also using in my research, and his books as the textbook in my classes. So really, his work has been very close to my heart. And of course, then we have met in different conferences, and we have talked a lot, and we have discussed a lot of things. So that's happy birthday, Doc, and thank you very much for all the contributions that you have made to this area. Okay, so with that introduction, I like to borrow some of this, part of the title of Doug's book, which is Theory and Practice. So the topic of today's talk is going to be secure message transmission using multiple paths. But the emphasis is going to be how we move from theory to practice. So I'm not going to talk about any elegant or nice construction. The emphasis is that, okay, so now we have these nice results. How do we use them in practice? And I guess I hope to convey this, that this is going to be a very difficult task. And but if we do this, if you persist in this direction, then there are surprises and interesting things that we may get. Okay, so let's see. So this is, assume this is 2035, and so now we have quantum computers up and running, and everyone knows that now that we have to be really concerned because all the today's crypto, well, a public key crypto that we have is going to be vulnerable. They are not going to be secure. So we have to be thinking about alternative to this. We know some alternatives today, but the question is that what else? What are the things that are available when there is a quantum computer? If you want to have secure communication, this is a very, very basic secure communication scenario. So Alice wants to send a message to Bob, and there's an eavesdropper adversary. So this is the simplest case that we can imagine. So what can we do? And there are two main approaches that we can have. One is to share a key first, so establish a shared secret key, and then use that key to encrypt our message. Now, the second approach is to directly send the message without doing this shared key establishment. So just send in one go. But whichever you're going to take, I think the main thing is that we have to make assumptions. So, and if you can see here, it's obvious, because if Alice and Bob have the same power and the same capability as the adversary, there's nothing that can be hidden from the adversary. So we have to make some assumption. And this is the kind of assumptions that have been done in crypto, is common in crypto. The first one are computational assumptions. These are the ones that we use today. So we use for Diffie-Hellman, we heard, Noah-Schnorr, we heard. All of them use computational assumptions. We assume that discrete logarithm problem is hard, or factorization is hard, or some lattice problem is hard. That is one type of assumption. So it uses complexity theory to actually quantify it, but effectively those are computational assumptions. Now the second type of assumptions are quantum theoretic. So the one that we use in QKD. So we rely on uncertainty principle in quantum mechanics and say, okay, so now when we send a photon, this cannot be touched. And so these are theorems like no cloning theorem that we have in quantum theory that we use to have secure key establishment. So I think this big problem of key establishment or secure communication requires this assumption. The third type of assumption, which is maybe less talked about, is this physical assumption. So we make assumptions about physical world, about physical, this is called physical layer security. And that is what I'm going to focus today, actually. Now, this file security or physical layer security starts with pioneering work of Aaron Weiner. So he actually made this ingenious observation that if you have noise in the channel, you don't need to try to remove it to have reliable communication. You can actually use noise to have security. So this is completely different from Shannon's viewpoint. Shannon first developed coding theory to get rid of noise, and then he developed cryptography, right? He started secure communication. But in Weiner's case, Weiner said that, okay, no, the noise in the channel is a friend of cryptographers. So you can use that as long as you can assume that the noise in the channel between Alice to Bob is less than the noise in the channel from Alice to Eve, then you can amplify this noise to get a perfectly secure communication. Actually, epsilon perfect secure communication. So these are the measures of privacy, and this is the measure of privacy, secrecy, and this is the measure of reliability. So in one shot, we do both. We do both encryption and we do reliability. So reliable communication, both error correction and security comes in one go. And of course, this H is the Shannon entropy, and this is conditional entropy. Okay. So that is this. So the whole area of physical layer security starts with the work of Shannon, and this has attracted a lot of attention, not only in theoretical information theory community, but also in engineering and practical community, because you can actually make these systems. Because if you think about wireless communication, so the distance between sender and receiver, if someone is outside this building, the channel is going to be noisier to them. So this kind of assumption that that Weiner made do make sense in real life. So that is why, as I said, and also in theoretical viewpoint, it has some of the, still the general case of coding for this kind of channel is unsolved. So yeah, so I think this is a quite a remarkable model. The very nice thing about this is that there is no shared key. So you don't need to set up a shared key. The whole thing is a randomized coding. So Alice uses randomized coding to send a message, and the decoder can decode a randomized code. The security is tied to the physical environment, right? So it's not like a box that we can take it and easily move it. So we have to design, we have to know the environment. Okay, so that's in channel security. Now, when you go to networks, so in networks, a similar observation much later was made by Dolev, Dorff, Wartz, and Jung in '89, and then later they published their paper in '93, and then their work was refined by Franklin and yeah, I forgot the W. So the model was formalized. But the idea is that now if you have a network, so this is a network which is partially corrupted by the adversary. So the adversary has captured some of these nodes. The red nodes are captured by the adversary. So how do we, but the adversary hasn't captured all the nodes. There's a lot of nodes that are healthy. So how do we analyze this system? How can we talk about security in the system? And what they showed was what they did. They tried to make an abstract model of this network. And their abstract model was to show the network as a set of no disjoint paths. So you can see that we forget about all these intermediate links. And so we just consider the communication between Alex to Bob as done through this set of 3 no disjoint paths. So, and that is what they also called wires. Yeah, so this is one path, and this is another one, and this is the third one. So we can, from now on, we forget about networks. We can say that our network is now abstracted by a set of no disjoint paths, and this is like here. So so what I'm going to do today, I'm going to look at using this physical assumption for, and in particular, using multiple paths for providing post-quantum security or information theoretic security. And I'm going to focus on passive adversaries, simplest kind of adversary. And we will see that if you want to make these systems efficient, we have to do some modification that takes us to this, what is called moving target defense attacks, and then models. And then we will look at how implementation gives us, create side channels and the kind of issues that we have to deal with. Okay, so let's go back to, because this is our main model slide that you have to remember what the notation that I'm going to use. So this is the secure message transmission setting. We have replaced this network by this set of 3 paths, and you can see that only one of these paths is now seen by the adversary. In our case, we only consider passive adversary. So we call N wires, K of them are corrupted. In general, it can be actively corrupted. So in the case of the original model, it is actually a Byzantine adversary can completely corrupt the thing. So to send a message N, we have this secure message transmission encoding, which is a randomized encoder. It generates a list of components, n components. Each of them will be sent over one of these paths, and then decoder will receive a corrupted version of these things and decode some message in prime. So that's a simple encoder and decoder. And then we define security and reliability. Security is in terms of a statistical distance between, or total variation distance that I've defined here. This is this distance between two distributions. So the view of the adversary, when two messages that were chosen by adversary, one of them is going to be sent. So the adversary chooses two messages, M1 and M2. One of them is going to be sent. So what you would like to have is that the view of the adversary, so the adversary only sees whatever passes through this red line. He doesn't see anything else. So from this view, from his view, he should not be able to decide whether M1 was sent or M2 was sent. Okay. So, and then of course, this reliability is we want the original message to be able to be recovered. Now, efficiency, we also, as we said, we are interested in efficiency. So efficiency here is the blow up in the communication cost. So it is the number of bits that are transmitted divided by the size of the number of bits that we need to represent our message. Okay, so this is the original definition. And as I said, this area, the whole area of secure message transmission, also reliable message transmission, because we may forget even about security. We can ask the same kind of question. If we have a network that is represented by a set of no disjoint paths, can we have reliable communication? So the second part is just reliable communication. This part is secure, which includes reliability, secure and reliable. So this area was really motivated by a lot of work in multi-party computation, because multi-party computation requires all nodes to be connected to each other, and then in practice we don't have them. We don't have a complete graph, so we somehow simulate the perfect connectivity using this kind of message transmission. So it was the distributed systems is really built on this kind of work in secure message transmission. So lots of work in this domain, a lot of bounds to say. The important thing to note is that when I talk about secure message transmission, is not in general, it's just one phase transmission. It's not just sending from sender to receiver. These are interactive protocols. So there are multiple rounds. So you can see phase here is the number of interaction between sender and receiver. So here you can have one phase, two phase, and you can also have here one phase. And you can see that if you want to have this is perfectly secure message transmission. So zero error in privacy, zero error in reliability. If you want to have that, you should have at least your connectivity becomes 3K plus 1. So if K lines are controlled by the adversary, you need to at least have 3K plus 1 connectivity, which is a lot. And then if you're happy with epsilon and delta security, so you allow a little bit of leakage in quantifiable leakage and quantifiable error in recovery, you can have 2K plus 1. You can deal with less connectivity. And then you have bit efficiency. You have this kind of bounds. For both of them, you can see that there is at least certain amount of blow up in communication that you will have of redundancy because of the randomization that you're using in the encoder. Okay, so these are lots of work in this domain, and then there are lots of constructions, many elegant constructions. So the construction, for example, the construction that uses the optimal construction that we have for, if you want to achieve if you want to have a perfectly secure message transmission for 2K plus 1 connectivity, that was an open question for maybe 50 years. So I think maybe more than that. Yeah, so I think Kurosawa and Suzuki had the first solution to this in 2000, around 2006-7, and then recently they have another construction that I've seen. These use very elegant construction in codes and coding theory. So quite nice, complex decoding algorithms. So there are lots of, as I said, theoretical work. And also extension. So people have looked at the case that suppose we allow a small public channel, low capacity public channel, in addition to these lines that connect sender and receiver, suppose we allow a little bit of reliable public communication, how this bound changes and what can we gain. So people have tried to look at variations that can make sense in practice. Okay, so now suppose we want to use them in practice. What do we do? So we have all these whole plethora of construction, beautiful, optimal construction. Which one are we going to use? And I think it's the first thing is that we have to forget about multi-phase communication, because no one is going to accept in networking community, because now we are talking about real network we want to actually implement. So no one is going to accept a message to have an interactive round to have one message sent. So we forget about that part. So we just say, okay, so let's just focus on one-phase communication. So only one coding will happen and we send it to the receiver. So of course, if you have two or more phases, you also have these issues that you have a stateful attacks, and the protocol becomes a stateful and you have problems. So that's not good anyway, so forget about that part. We also are going to forget about perfect security and perfect reliability. That requires too much connectivity. We cannot afford that. So let's start with, but we need this much. So this is required, 2K plus 1 is required even for only reliability. So we stay with that. And we also are going to have even a further, as I said, a further assumption. We're going to say that adversary is actually passive. So it's not going to corrupt things. So, and I think it's not too much simplification. So it is in real life, adversaries are active, but it's also a passive attacker does make sense, because in many, what they call this, advanced persistent threat attacks. So the adversary stays dormant in the network and collects information. So actually dealing with those types of attackers are in many cases very, very hard. So it is good to actually try to make the life of that kind of adversary. So these are adversaries that stay for years even in the network. So make that one provide protection against them. So this study of for passive security actually does make sense. So this is where we are. So now we have a multiple path. Alice and Bob are, this is our network. So we have found 5 wires, 5 paths, no disjoint path in our network. 3 of them can be paired by the adversary. So one in this particular example. So the question is that, first of all, how large K can be? So in the setting of passive adversary, how much corruption we can tolerate? And it's not hard to see, it's easy actually to see that you can, as long as one of the path is not seen by the adversary, then we can be fine, right? So as long as the adversary cannot see all the path, we can have a very simple encoding that something like this, randomized encoding that takes a message M, it randomly selects n-1 random strings, the same length as the message, and then the last component is going to be M minus the sum of the previous one, and now we have effectively a NN secret sharing scheme. So we heard about secret sharing scheme today, but this is an example of a simplest secret sharing scheme, N1. So you need all shares to be able to reconstruct the message. So the encoding is simply like this. You can see it's very fast, extremely efficient. Receiver can do exactly the same. So the receiver has to add all of this together and recover the message. Just remember that this is a passive adversary. So one issue that exists here is that now the cost, the communication cost is too high. So because now we had a lot of, suppose from Calgary to Toronto, there are maybe 100 paths. And so I have to, if I use this model, it means that for every bit that I want to send, I have to send 100 bits. So the question is that, can we do can we become more efficient? And I guess, as you can imagine, that if we can bound the adversary's power, if you can say the adversary can see only K wires, and K is less so, in our case, between Calgary and Toronto, instead of there are 100 paths, and then 10 of them, up to 10 of them can be controlled by that, can be seen by the adversary. Then we can, instead of sending the message on all paths, then we can choose a random subset of K plus 1 path and use a K plus 1 secret sharing scheme to generate shares for that smaller subset. And of course, so I haven't told you how we are going to let the receiver know which subset you're choosing. So that's we're going to see a bit later, but that can be done. So now effectively, now we have, I should say, it should be K plus 1. So now our efficiency improves. Now we have to send, instead of 1 bit, I have to send K plus 1 bits. So that's a good start. But we cannot keep that the subset fixed. So if I have a sequence of messages that I'm sending from sender to receiver, I cannot keep it fixed, because if I use always the same random subset, then the adversary over time he can probe the network and he can find out. So you can there is no question that subset, there is nothing that stops the adversary to learn. So now we have to actually move so we have to change our subset. So for every message that you are going to send, we have to choose a new subset of K plus 1 messages, K plus 1 subset of wires, and send our messages over, send each message over the corresponding subset. So effectively, when we look at the sequence of messages, our encoding is going to look like this. So for the first message, so in general, the principle is that for every message that we are going to send, we are going to append to it the information about the subset that we are going to use for the next message, right? So our first message is going to use the full NN secret sharing scheme. And in that message, we are going to tell the receiver what subset will be used in for the second message. And from then on, every message is going to be appended with the information about the subset that will be used for sending the next message. So our communication blow up is going to be more, increase a bit. So we have this K plus 1, a bit more, but it still is quite a good system that we have. Okay, so that is, now we have a, what can we, so we are good in terms of how sender behaves. So what about the adversary? So the adversary can also move in the network. So we should also let the adversary to do the same thing. So the adversary also is going to change the subset that is going to observe. So every time slot is going to observe something different, a new subset. So it's going to look something like this. So this is our KK secret sharing scheme gave us the shares. The shares are sent. The adversary chooses a subset of its own. And then the next time slot, the the sender chooses another subset, and then also the adversary. So this is how the two move in the system, and that is what is this in the security community, what they call moving target defense. So you move, the goal is to move the target for the attacker so that the attacker can always stay one step behind. So that's the idea. So what can we say about security? So now our system we have is a time varying system. So we did something from the information theoretic part. We are sure that if the adversary doesn't capture all the paths that carry the information, we are going to be fine. But what about this time variation in the system? How we are going to model that one? So this is where we use this model, that Markov modeling of moving target defense gains by Martin van Dijk and his students and colleagues. So they effectively, what they did, they analyzed this moving target defense system, and one way that they modeled it was by Markov games, a randomized Markov game between an attacker and a defender. The state of the system is represented by a matrix M, which is the state transition, and it takes the state of the defender and the state of the attacker into account. So MD and MA are the transition matrix that the defender uses, and the attacker, and MA is the one that attacker uses. And these two, lambda and mu, are the probability that the two move in a particular time slot. So we allow them to move or with some probability. So, and they said this is the way that the system is modeled, and the way that the system progresses is this by randomized strategies. So the strategies are random. And the success is going to be we're going to measure security by the probability that the attacker succeeds in a time in t time interval. So that's the success probability. That's the measure of security. So this is how their modeling works. So we use exactly the same framework to show our system, to analyze our KK secret sharing scheme. So now the attacker, the sender is used as a KK secret sharing scheme. So I'm not going to say K plus 1 because there's no difference. So we just use KKs for simplicity of notation. And then you will see that we can use their states, is that this zero state is where the attacker doesn't know any of the path. State 1 is when the attacker has learned one of the path, one of the wires, state 2 and so on. State K is when the attacker has learned all the paths that are carrying information, and that stage the attacker is successful. So this is what the analysis that we did, and we published a year after their work. So we can define now these MTD games. So the games we can have different kinds of games. So defender moves, changes U path in each time interval. The attacker changes V path, and then now we can also have a variation of attackers that the attackers that want not to be detected. So we have if the attacker moves a lot, it can be detected. So there is a threshold tau we can introduce in the system. And we consider two types of attackers: risk-taking attackers that move with the highest probability that they can afford, and then risk-averse adversary that they try to stay below the threshold detectability of the system. So these are the kind of, so this is a very simple case, so game 1-1, which means that in each time slot, the defender changes one of the path that it is using, and the attacker actually changes one of the paths, changes one randomly, one more of the remaining path, swaps one of its paths. So, and this becomes like a transition probability that you can for the two cases, risk averse and risk taking adversary, that you can, it shows how the system at the state 1, the state I, can move to a state I plus 1 or I minus 1. So the attacker has captured I wires in one time slot, can move to the next one, become more, to capture more things, or it can lose something, or it can stay in the same state. So that becomes our transition matrix, and now we can actually show that this we can have this theorem that expected number of compromise in the first time intervals is going to be something like this. And so it becomes just effectively analyzing this Markov game and then looking at the transition matrix. So the other measure that we introduce is the expected number of steps for the first time that the system is compromised. So expected. So the more number of steps we have, the more secure our system is going to be. So we have these two measures, and we can show theorems for both of them. And so these theorems are all these expressions that we can actually do. These are numeric simulation of those numerical graphs that graphing those numerical results. So, and what you can see here is that as we expect, as the probability of changing path increases, the success probability is going to decrease, and also the number of steps that is required for the first compromise of the system increases. So it looks like, okay, so actually the model at least matches the intuition that we have in the sense that if we change the system a lot more often, then it's going to confuse the attacker more, so the attacker will have less chance of being successful. But the problem, so this really is a bit was bothering me because it does not take the cost of this movement of the system, movement of the path in the system. It looks like, if we do for every message, if you change all the path, you're going to be better off. In practice, anyone who works in networking, they know that you cannot change your routing table and switches and instantaneously. So this is really not really meaningful analysis of the system. So it shows something, but it doesn't show the whole story. So that is where so I thought that we should try to understand the cost. If you want to refine our model, we should try to understand what is the cost. So where the costs occur and how can we actually model it in our games. So that's what started my collaboration with the networking people in our university, and also Northeastern and MIT Lincoln Lab. So I think this is what we started to understand these things. So we believe that this is a good system because, as I said, it's a very nice, it gives you post-quantum security, and it's so efficient that it's really, it can be really useful in many application settings. It may not be the only one, but it can be it can become as part of your arsenal in going to post-quantum secure system. So let's see. So this is what so now this discussion has started. So between us who are doing the crypto part that have designed this and analyzed the system, and then the people who were looking at the implementation of this. So we had to have a simulation and implementation. The question was, okay, so this was a model that we had analyzed. There were a set of lines. So what should we implement? So what is a line in real life? And what is the meaning of capturing a path right? All in theory, we just said capture a path, but how do we implement these things? So this had a lot of discussion, and then after we all agreed that, okay, so in the end, in fact, if you want to simulate or make a test bed, we have to have a set of nodes. The path is not going to be a line, it's going to be a set of nodes that are connected by links. And then attackers in practice, so this is again something that was a topic of a lot of discussion. So the attacker is going to capture nodes. So that is what we ended up agreeing on. And I think now with this, some of the analysis that we had are not going to be directly applicable. So we should now decide how re-evaluate the system in this new experimental setting. So attacker captures packet at nodes. We agreed on this. The attacker can. So we assume that we again agreed upon that the attacker can access all the nodes in the network. So that's fine. But we limit them to capture capture K at a time. And there are good reasons for this. So if you want to access the node, if you want to extract information from them, if you have, I mean, you can argue that this is such a bad assumption. So that's what you can do. And so we implemented, actually not we, I guess the networking group and system group, they implemented both in a simulation environment, Mininet, and also we created a real testbed with switches, and we did the physical evaluation of the system. And this was months, so the whole summer. And in the end, we concluded that the measuring of the cost that was the first goal was not possible. And the reason that it was not possible was that in the simulation environment, you can really not measure the cost because you are actually simulating everything. In the case of physical networks, again, you couldn't measure the cost because the switches that we had were all modern switches and they were very fast. You couldn't generate this. You couldn't really measure the cost that was that we expect to exist in a system. So it was effectively, from that angle, what we did was not really successful. But we learned a lot. So including, for example, that all the analysis, that Markov analysis that I showed you, they required that, so it meant that the attacker and defender do their actions simultaneously. So the attacker chooses this many nodes, at the same time, the defender chooses this many nodes, and then the attacker does at the same time. So, and that is not really, this synchrony doesn't happen in practice. So, and then, so we did some measurement of how this, not the attacker's action and defender's action being synchronous, how much leakage it generates, and by measurement of how many messages that the receiver or the attacker could reconstruct, we could actually find this, measure the amount of leakage. But I think so that was the part that was, in some sense, not very successful. But really, what it gave us, it was this observation. It's a very important observation that was actually made again by one of the students who was working on the implementation. And that was the observation was that now the length of this path that is not in the model is actually important. And we, in the basic model, every path is the same, is a wire. But in practice, because these wires, the paths are a sequence of links, their length becomes important. So the longer path will keep a share for a longer period of time in the network. And that gives the attacker more chance to capture those shares. And that is where what we call data remnants, network data remnants attacks, so the data that remains in the network. And so that is where Actually, we published our paper last NDSS. So it's to show how it works. So this is like you can see that the shares are sent across those three paths. The adversary at the same time interval captures those three. So it captures two of the shares. The top share has stayed safe. For the next one, the adversary, the shares have moved one more clock, one more link in the network, and now the attacker knows that these are those nodes cannot carry the shares. So that he's not going to look at those nodes. So he's going to the only nodes that are at distance 2, I mean distance, the number of links from the sender are those 3, and so the attacker actually can capture the system, the message. And the success probability becomes 1. So despite theoretical security, you can see that in this case, they completely breaks the system. So, and this particular NDR attack, this what we also call the side channel attack. So this exists in all networking protocol, or all these protocols, cryptographic protocols that have this model of path as wires and do not consider actually nodes in the network and use secret sharing. Okay, so we wanted to see, at least to understand a little bit more about how this, so what happens in this, so to calculate some probabilities and do some experiments. So we refine the model. So now there is we introduce this notion of clock tick. So at each clock tick, shares move one link at a time through the network, and so these clock ticks are as regular intervals, and we, for simplicity in our experiment and for our measurement, we assume that the length, all the paths are the same length, but this, I think that was just for simplification. So, and our goal was to find that success of the adversary for different strategies. So now the attacker, if the attacker knows that the system works like this, like the shares are sent and gradually they find their way through the network, one link in one clock tick, then the adversary can do different things. So these are the kind of adversaries that we considered, and they're not by all means complete. So the first one, the simplest one, the adversary captures a subset of paths and it stays on them. It doesn't move. The other one, which is, it moves in a synchronized way. So synchronized means that in each clock tick, the shares move in the network one step, and then the adversary at the same clock tick, it actually selects a random subset itself. So, and we also consider the case that they are not synchronized. So the adversary can move in the middle of a clock tick. So in the case of synchronized one, we also consider blind attackers that randomly selects a subset of nodes, and then planned attackers that takes into account how far the time is. So it knows that all the previous nodes are not useful to capture because the shares have moved through the network. So we should not look at them. So these are planned attackers. So we actually did these calculations, and you can see that so there are the probabilities that we have found for these attackers, and when you graph them, you can see that in the planned attacker case, as this is the length of the path, you can see that the probability increases, and effectively you can capture the data leaks through the network. So this is the probability of capturing, recovering the data by the attacker. This is the length of the path. Okay, so now we see that it seems that everything that we did is not going to be useful. So they're all not so there's this side channel attack that we somehow have to deal with it. So the question was how to work around it. And one mitigation that we found as our first solution was to generate more shares and send them in a planned way, so not at the same time. So it's a kind of spreading our shares over time and space. So instead of, in this case, for example, we have 2 shares. So we have so we only need 2 shares. So k is equal to 2, but we generate more shares. So we have a factor of h, which is 3. So instead of 2 shares, that was enough. We create 6 shares, but these 6 shares are not sent in one go because you may not even have that many paths in the system. So what we will do is send them, the first 2 are going, and you can see that in each time, in each clock tick, the yellow ones are the ones that are shares that are sent through the network. The red one are the subsets that are captured by the attacker, and this bottom one shows here the subset of the captured shares. So as time passes, you can see that share 1 and 2 have moved 1 step. Now share 1, 3, and 4 are introduced in a different subset. The adversary has chosen 2 new nodes to capture. And then in the third time slot, again, has things have moved through the system, and the new share, the last 2 shares, 5 and 6, are introduced in the system. And the other one have moved, and the attacker has also captured things. So you can see that in fact, now we can see that the adversary is going to has lost the chance to capture S3. So he's not going to be able to recover the message. So effectively, spreading your shares over time and space gives makes the life of attacker much harder. So we analyze this, and actually it shows that it effectively does achieve the promise that it has. So this is with countermeasure. You can see that these curves move downward. The same with countermeasure. These are the length of the path, which is 6, and this is the length of the path, which is 5. Okay, so these are, as I said, this is a very basic countermeasure, and that takes me to the concluding remarks. So, when we do cryptography, we have these idealized models, and which is we try to balance details of real world with we do not capture a lot of details because we can, if it's too complex, we cannot analyze it. So we try to simplify and make an abstraction for real life. And so what I showed you is that these kind of abstractions, although it can generate a lot of very, very great understanding of things and very interesting results, computer challenging and questions, but then when we want to bring them into real life, then it can create a lot of new challenges. So in our work, there are many new questions, right? So how do we analyze this MTD gain for more general cases, or how can we really, so I only showed you some attack strategies. What are the other attack strategies, real attack strategies that the adversary can use, and what are the targeted attacks that can be launched against particular messages? So there are many related questions that can be solved in that domain, looked at in that domain. So with that, I guess I just wanted to have to give you some final thoughts on theory and practice. So this is a quote by Ahu and Allman. These are the operating system Turing Award winners. Computer science is the science of abstraction. So we can say the same thing about about cryptography, the science of abstraction, that we make abstractions. And I think this abstraction existed, or actually dealing with these models, building a model and looking at them, is not just computer sciences. It existed many years before that by Lord Kelvin, that wanted to make a mechanical model of how things work and to be able to understand them. And I guess this comment on these models so this one is by again, Nobel Prize winner in biophysics or something, biochemistry. A theory has only the alternative of being right or wrong. A model has a third possibility. It may be right, but irrelevant. So, and then the famous quote by that the model can be, so it can be, you have to see how wrong they can be that they are not useful. So again, we learn a lot from them, but how wrong it can be that not be useful. So I think these are something to think about. And that's it. Thank you.